Welcome to my channel. In this video, we are going to walk through an examples on a Butterworth Bandpass filter using the parallel coupled lines. So before doing anything, let's revise what we have learned. So the very first thing that we need is to understand the procedures for implementing a Butterworth Bandpass filter. First, just like what we have done in the last video, we need to know the order of the filter, and we need to calculate the fractional bandwidth. Sometimes the question may not be that straightforward, so we need to work it out. And we can either use the prototype tables to obtain the G values, or equally, we can use the following formula to calculate it. The formula for Butterworth Bandpass filter would be very simple. It's this one here. G of k is equal to 2 times time and then backtrack, and then 2k minus 1 pi divided by 2n. And the next thing that we are going to do is to use the G values that we obtained from step 3 to calculate the immersion impedance, J Z0. The formulas are here. The start stage and the end stage have their own formula, but their formula are very similar. Yeah. And the middle stage, we are going to use this formula to calculate the J Z values. And with this value, J of Z, we can calculate the even mode impedance and odd mode impedance for each of the stages of the filters. The formulas are given here. The even mode impedance and the odd mode impedance. Now, let's take a look at an example. We are going to design a Butterworth Bandpass filter based on parallel coupled lines technologies. And the filter has to satisfy the following specifications. The order of the filter is 3, the lower corner frequency is 3 GHz, the higher corner frequency is 3.5 GHz. Okay? So let's start our business. Now, we already know the filter, the order of the filter is 3. And we need to know the fractional bandwidth. We know the lower corner frequency is 3 GHz. The upper corner frequency is 3.5 GHz. So from here, we know the resonant frequency. The resonant frequency is the square root of the product of this lower and upper corner frequency. So 3 times 3.5. So whatever, yeah. The value should be 3.24 GHz, and from here we can work out the fractional bandwidth. The fractional bandwidth is the actual bandwidth divided by the resonant frequency. So it is 3.5 minus 3 and then 3.24, and based on my calculation, and this is going to be 1/4. So this is the fractional bandwidth. It's about 15.4%. Now the next thing is to calculate the G values. You can work it out for me in here. So G1 is equals to 2 sine 2 1 minus 1 pi and divided by 2, and n is 3. So this will end me up with 1. And G2 is sine, and then 2 minus 1 and this will be 2, and G3 is 2 times 3 minus 1 and this will end me up with 1, and G4 is equal to 1. So basically we have all the G values, and the next thing that we are going to do is to work out the J Z0 value, the inversion in parameter. So we have the G value the G value is equal to 1, 2, 1, 1, and the J Z value is here in this column. The formula for the first one is so if you work it out carefully, oh, 15%, then we'll get 0.4923, and similarly we have to use the we are going to continue with this process. Pi, the formula is different for the middle stage, and is going to be 1 and 2. So, yeah, it's not that way. It's pi d 2 0.1543 times 1, right? I don't want to write it. So if you do it carefully, it's going to be 1.713. And for this one, and we can say the period stage, so it's also like this. Yeah, I got it wrong here. Yeah. This one should be 2. So if you do it carefully, you will get 1, 3. And this one here, the formula should be similar to the one for the start stage. So the value should be consistent. Now we have already got the value, the J3 value. The next thing that we need is to work out the even mode impedance and odd mode impedance. The even mode impedance can be calculated using this formula. The odd mode impedance is okay. So let's work this out. If you substitute this value into this formula, you will end up with 86.735. And if you substitute this value to the second formula here, you will end up with 37.5. And if you continue with this process, you will get 60.38 and 42.399. And similarly, you will get the same value for stage 3. And for the last stage, you will get the same value as the one for the first stage. So this is what you are going to get. And with this value, this is enough for you to design a filter. What is missing here is the actual length of the parallelized coupler. I can tell you, you can just simply find the quarter wavelength. So for example, in this case, the length here is L, and quarter wavelength is the guide wavelength divided by 4. because we are now trying to use ideal coupled lines rather than microstrip or coplanar coupled lines. So we can just simply use C as the propagation velocity. And the frequency will be 3.24 gigahertz as we have done before. And times 4. So from here, if you do it very carefully, you will find the length of the resonator. It should be 23 millimeter. Okay, I hope this is going to be helpful. Now, with all this value and together with the length, then you can just design a filter. You can just implement the filter. But instead, I'm going to show you how we can use the public domain software to implement this filter. So I'm going to switch you to another window. Okay, this is for one. So now let's take a look here. Let's take a look in the example that we are working on. So I'm going to delete all of them first and start the design from scratch. And fortunately, with Code Studio, or the present name of the software is called syms. You can do everything automatically. Say in this case, you can use filter synthesis tools, which is one of the tools under the pull-down menu under the tool tabs. And you fill in the form. The methodology that we are going to use is lateral coupled transmission line. The filter type is Butterworth. Right? You can choose other types as well, but for this question, we use Butterworth. The frequency 3 gigahertz as a lower corner frequency, 3.5 gigahertz as a upper corner frequency. The order of the filter is 3. The characteristic impedance is 50 ohm. The filter is going to be ideal coupled line technologies. So we just synthesize this straight away. Okay, so we just copy and paste. So this is the filter, and you will notice all the impedance that is generated. Each of the impedance that is generated for each stage will be exactly the same as what we have calculated. Even there may be a difference, but it's just numerical error. Like say for example, in stage 1, according to what we have calculated, we got 86.73, but the software ended up with 86.66 for the even more impedance. The output impedance is 37.5 by calculation and by software generation. And the length of the coupler will be the same for all stages, 23.0. According to my calculation, is exactly 23 millimeter. So the builder apparently, exactly what we want. And if we simulate this circuit, then we will get the gain, the filter insertion loss, according to the simulated result. It's like this. And the match is indicated by the blue curve here. And also I want to show you the Smith chart. The Smith chart will display how close the impedance locus, and the impedance locus at the center is the 100% represent the 100% match. And in this little loop here, we will have the impedance closely matched enough, but they are not exactly matched. But this is good enough for wideband matching. This is a very good quality match, and you can see from the S11 of this graph. Okay, so this is all I can show you in this occasion. If you have any question, please leave your questions to the comment section of this video. Thank you.